Let's talk about something that happens inside your computer every single second. Something that's so fundamental, so ingenious, you probably never even think about it. We're going to look at how your operating system manages memory.
And we're going to start with a puzzle that seems to, well, break the laws of physics. Have you ever looked at your system monitor and noticed that your open apps are using, say, 12 gigabytes of memory, but you know for a fact you only have 8 gigs of RAM installed? How is that even possible? What is going on there?
Well, the answer isn't magic, even though it really does feel like it. It's actually a very sophisticated illusion, a clever trick that underpins all of modern computing. So stick around, because we are about to pull back the curtain and show you exactly how it's done.
Okay, so at the very heart of this whole problem is a basic conflict. Your computer has a fixed, finite amount of physical memory. But the software we all run, it has a nearly infinite and totally unpredictable appetite for it.
And here's where the real problem lies. Physical memory, your RAM, is kind of like the computer's workbench. It's super fast, but its size is limited. Your applications, on the other hand, are the projects you want to put on that workbench. You might open an image editor, and it starts out small, but then you open a gigantic high-res photo, and suddenly it needs way more space. The operating system can't just throw its hands up and say, sorry, workbench is full. It has to have a much smarter plan.
So how did we get here? Well, the very first operating systems had to figure out how to get multiple programs to share that limited workbench. And let's just say their first few attempts were pretty basic.
The first and most obvious idea was something called partitioning. It's exactly what it sounds like. You just chop up the available memory into a bunch of different sections, and you give one section to each program that needs to run. Simple, right?
Well, this simple approach had some really big flaws. If you used fixed-size partitions, and your program was smaller than the chunk you gave it, you wasted all that leftover space inside the partition. We call that internal fragmentation. So you think, okay, I'll be smarter. I'll use variable-size partitions and give each program exactly what it needs. But then as programs open and close, you're left with all these tiny, useless gaps between the programs. That's external fragmentation.
So, either way, you end up with the same mess, fragmentation. Your memory starts to look like a block of Swiss cheese, just full of holes that are too small to be useful for anything. This was super inefficient, and it was a clear sign that a completely new way of thinking was needed.
And that better approach, well, it was a total game changer. It was a complete paradigm shift called virtual memory. And it's the foundation of every single modern operating system you use today.
The big breakthrough was to stop thinking about memory as one thing. Instead, they created two different concepts. There's the physical memory, the actual RAM chips in your machine, limited, expensive, but fast. But then, each program gets its own logical memory space. This huge, private, expansive view of memory that can be much larger than the physical RAM. Most of this logical memory actually lives on your slower, but much bigger, SSD or hard drive.
So how do you connect these two worlds? The magic ingredient is a process called paging. Here's how it works. The operating system takes a program's giant logical memory and breaks it into small, fixed-size chunks called pages. Then it divides the physical RAM into identically sized chunks called frames.
This is so clever. Because all the pages and frames are the same size, any page can be loaded into any empty frame. The different pieces of a single program don't even have to be next to each other anymore. The OS just keeps a little map for each program, it's called a page table, to remember where all the pieces are. And just like that, the fragmentation problem? Gone. It allows for an incredibly efficient and flexible use of your physical RAM.
And I mean, you cannot overstate how huge this was. As the computer scientist William Stallings put it, with virtual memory, one of the most fundamental restrictions in all of programming had just been lifted. For the first time, a program could actually be larger than the computer's entire physical memory.
So, okay, the idea is absolutely brilliant, but how do you actually make it work in the real world? How do you make it fast enough to be useful and safe enough to be stable?
The first piece of this puzzle is something called a page fault. Now, that sounds bad, right? It sounds like an error, like something crashed. But it's not an error at all. In fact, it's a totally normal, routine signal. It just happens whenever a program needs a piece of its memory that's currently living on the disk instead of in the fast RAM. A page fault is basically the program raising its hand and telling the OS, hey, I need you to go grab that page for me.
This whole process is often called demand paging, and it's how the OS juggles everything. When that page fault happens, the OS steps in. It pauses the program for a split second, finds an old, unused page in RAM, saves it to the disk if needed, and then loads the new page the program asked for into that now empty frame. It updates its map, and the program just continues on, completely clueless that this tiny, high-speed swap just happened behind the scenes.
Of course, there's a catch. If you don't have enough physical RAM for all the active parts of your programs, the OS can get overwhelmed. It ends up spending all of its time just swapping pages back and forth from the disk. This is called thrashing, and it's the reason your computer can slow to an absolute crawl when you're low on memory. The system is spending more time managing the illusion than it is doing any actual useful work.
So to make this whole system fast enough, computers have special hardware. See, every time the OS has to look up a page's location in that page table, it's a relatively slow memory access. To fix this, there's a tiny, high-speed cache right on the CPU called the Translation Look-Aside Buffer, or TLB. Think of it like a cheat sheet. It stores the most recent lookups, and because programs tend to access the same few pages over and over again, most of the time the answer is right there in that super fast cache, which lets it skip the slower lookup process.
Okay, so we've made it fast. But what about making it safe? I mean, with all these different programs sharing the same physical RAM, what's to stop one buggy application from accidentally writing over the memory of another program, or even worse, the operating system itself, and crashing the whole machine?
The answer is privilege levels. Your computer is basically always running in one of two modes. Your applications, your web browser, your games, your text editor, they all run in user mode. Think of it as a protected sandbox. They have restricted access and can't directly touch the hardware or another program's memory. The operating system, though, it runs in the all-powerful kernel mode. It has the keys to the kingdom. So if an app needs to do something privileged, like save a file to disk, it has to formally ask the kernel, who then acts as a gatekeeper, checks the request, and performs the action for it. This is what keeps one bad app from taking down the whole system.
All right, so let's bring it all together. Let's look at how all these different pieces combine to create the seamless multitasking experience that we just take for granted every single day. These are really the 5 pillars that make it all work. You have virtual memory, which creates that illusion of infinite space for every program. You have paging, which uses the real space efficiently and gets rid of fragmentation. Demand paging keeps only the necessary stuff in your fast RAM. The TLB makes all the lookups lightning fast. And finally, privilege levels keep everything secure, stable, and playing by the rules. And that's really the secret, isn't it? It's this beautiful, multi-layered system of illusions, rules, and hardware assistance that lets our devices perform these feats that seem totally impossible. It's what creates an experience that's smooth, stable, and incredibly powerful.
This system has served us incredibly well for decades, but the demands we put on it are always increasing. Which leaves us with one final question to think about. As our programs and our data sets become ever more massive, what brilliant new trick, what next great illusion will computer scientists need to invent for the next generation of computing?